Well, this is the second demo I made for the TechArt class. For this demo, I used Computer Shader to create a real-time path tracer which supports sphere and triangle-based geometries, a couple of different materials, and a depth of field camera effect. So the intersecting methods of sphere and other triangle-based geometries are separated. For spheres, it's much efficient if we use this simple mathematic method. No matter what the size is the sphere, we only have to calculate once. However, for other types of geometries, we have to calculate for all the triangles, let alone that the algorithm is already more complicated than the sphere. And there are four kinds of materials that are supported by this path tracer: matte, metal, glass, and emission material. For a matte object, when a light ray hits the surface, we have to randomly choose the light ray's reflected direction, because on a microscopic scale, a matte object surface consists of an infinite tiny microfacets that are chaotically aligned, so the reflected rays go everywhere. For metal objects, it's the opposite case. The reflected ray goes to the symmetric direction of the incident ray. We could also randomize the reflected ray a little bit within the normalized sphere, so it becomes rough but still looks like metal. A glass material can be a little tricky because it splits the incident ray into two parts: reflected ray and the refracted ray. And we can only trace one ray at a time, so here we use Fresnel factor and a preset value to determine which part we should trace. The emission material is easy. All we have to do is to accumulate its color when the light ray hits its surface and stop tracing the ray, because in real life a light source is where the light rays come from, so when a light ray hits a light source in ray tracing, it should be stopped. Depth of field is kinda like supersampling, which is used in anti-aliasing. The difference is that supersampling samples several more times within the pixel, while depth of field samples several more times within a much larger region, which represents the camera's aperture. So supersampling only makes a small area around the edges blurry to achieve anti-aliasing, while depth of field makes a larger area blurry.